Since we know a bit about molecular orbital diagrams as well as how to calculate bond order, let's look at all of the homonuclear diatomic molecules for the elements in periods 1 and 2. Period 1 contains hydrogen and helium, so let's start there. For hydrogen, we can see that there are 2 electrons in the bonding orbital and none in the antibonding orbital. That gives us a bond order of 1, which is why a single bond will form between the hydrogen atoms. For helium, we have 2 electrons in the bonding orbital and 2 in the antibonding orbital. That gives us a bond order of 0, which is why diatomic helium will not form. Now let's move to period 2. That would be the elements from lithium to neon. In order to determine the bonding behavior of these hypothetical molecules, we would simply place the valence electrons in the resulting molecular orbitals from lowest energy to higher energy. However, there will be some differences in the order of the orbitals depending on the atoms involved. Looking at this diagram, we can see the molecular orbitals that would result when 2 atoms of these various elements come together, and also that there is a discrepancy in the order once we get to oxygen. The sigma 2p and the pi 2p orbitals occur in a particular order from lithium to nitrogen, and then they swap from oxygen to neon. This occurs because of a phenomenon called sp mixing. This is when the sigma s and sigma p wave functions combine in such a way so as to affect the stability of the corresponding orbitals, and places the sigma orbitals higher, both the bonding and antibonding. Notice that on the right, the sigma p orbital is now above the pi p orbitals. Once again, this will occur for oxygen, fluorine, and neon because of the heightened energy in the 2p orbitals due to the presence of paired electrons in those orbitals. In general, the energies will decrease as we move to the right because the effective nuclear charge will increase as we add protons to the nucleus, which will cause the atomic radius to decrease. If we place all the electrons in their orbital diagrams, we could calculate the bond order for each molecule, which would give us these values. For Li2, we get a bond order of 1, which means a single bond between the atoms. This makes sense, as they each have 1 valence electron. For Be2, we get a bond order of 0, which means this molecule will not form. For boron through fluorine, we see the bond orders we might expect, especially for nitrogen, oxygen, and fluorine. And for neon, again, we get a bond order of 0, which means this molecule will not form, which is to be expected since neon has a full valence shell. These diagrams provide insight that goes beyond what we can see with a Lewis dot structure. Therefore, molecular orbital theory provides our most advanced understanding yet when looking at chemical bonds.